Packaging and integrating and future of power electronics. Challenges for power electronics: increased power densities, higher efficiency, lower electromagnetic emissions, increased robustness, modular plug and go systems, lower cost. Performance targets and constraints: cost density, efficiency, power density, robustness. Power targets are reliability or availability, energy efficiency, power quality, mission profile, weight, volume, through life cost. Meeting the challenges. Emphasis of one design criterion may adversely affect others. Converter packaging. Typical power converter consists of semiconductor power modules, a physically separated DC link, a separate input and or output filter, EMI filter, gate drivers, controllers and sensors. Demarcation of technological disciplines means electrical, mechanical, and thermal aspects are treated separately by separate teams. Each component is designed separately, cooled separately, and has its own operational requirements. Integrator opportunities. Integrator passive components, gate drivers and health management, power module, die and packaging materials, integrator thermal management. Heat transfer limitations. Natural convection heat transfer coefficient 3 to 25. Array heat transfer coefficient up to 200. Forced convection 10 to 200. Array heat transfer up to 1000. Forced convection heat transfer coefficient 50 to 10,000. Array heat transfer coefficient up to 50,000. Condensing steam heat transfer coefficient 5,000 to 50,000. Boiling water 3,000 to 1 lakh. Combination of solid conduction and convection heat spreading limiting thermal resistance increases with heat source size. Convection high film heat transfer coefficients eliminate the need for adding heat spreading. Integrated cooling target overall reduction in weight and volume for liquid cooled systems. Comparison of cooler options. Conventional base plate and separate cold plate. Integrated base plate impingement cooler. Direct substrate impingement cooler. Direct substrate impingement cooler with optimized spray plate. Integrated cooling comparison. Cooler type, cold plate. Specific thermal resistance 63.52. Base plate impingement special thermal resistance 45 point. Substrate impingement special thermal resistance 38.59. Direct targeted substrate specific thermal resistance 30.39. Cooling solutions compared its same specific pumping power. Thermal integrator summary. Thermal path design is dictated by the cooling medium. Air-cooled designs will always benefit from heat flux spreading, solid conduction or two-phase. Heat spreading is more effective for smaller heat sources. Partitioning of modules into smaller blocks permits lower thermal resistance. Solutions will be bulky for solid heat spreaders. Cooling methods with higher effective heat transfer coefficients can be applied without flux spreading, where H is greater than 10 kilowatts. For typical substrates, lower overall thermal resistance, compact, scalable solution but needs secondary heat exchanger. Some designs have high pumping power requirements. Electromagnetic management. External parasitic RSLS. Internal busbar and substrate parasitic LWB, RWB, LSP, CPP, CP plus CP. Filter component CINT, LFCF. Impact of module layout and partitioning on parasitic inductance. Potential for inclusion of filter components like commutation loop decoupling. Layout optimization. 4 title half bridge module 140 square. Option 1 tiles configured as switch and APD with common busbar and terminals. LS equals to 11H NH. Option 2 tiles configured as half bridge with common busbar and terminals. Option 3 tiles confirmed as half bridges each with separate terminals. Integrated passives. SiC or GaN devices produce fast transitions and have low output capacitance. Good decoupling essential. Possible output filter to reduce EMI. Impact of integrated decoupling. 100A commutative cell with split in use in 100 NH. Left figure without internal decoupling, right figure with internal decoupling of 200 NF. Voltage overshoot is significantly reduced by incorporating decoupling capacitance on substrate. Note: additional oscillations introduced between internal decoupling and external decoupling capacitance. Flexible modular communication cells. Smaller, high speed, low current modules in parallel to create high power converters. Optimized commutation paths, reduced parasitics, component electrical stress, inbuilt passive components, ability to interleave gate signals, flexible thermal management, novel packaging concepts. Advantages: building blocks approach to high power converters, contain the EMI at source, low weight solution, certification of different converters simplified. Conclusion: integrated modules based on functional commutation cell offers better electromagnetic performance and great flexibility in the choice of thermal management system. Mechanical partitioning of modules allow adaptation from thermal management. Electronical partitioning can aid electromagnetic management and increase control flexibility. Integrated passives, filter and close coupled gate drivers are essential to gain best performance on fast devices, etc. SIT and GAN. New assembly methods must be employed to achieve optimum thermal and electromagnetic performance with long life and extended rate thermal cycling. High level of structural integration demands multi-physics integrated design optimization. Thank you.